next paper is entitled Comparative Behavior of CO Adsorption on Rhodium on Alumina and Rhodium on Ceria on Alumina, Stabilization of Rhodium Dispersion by Ceria as observed using FBIR, Ron Dictor, Amico Research, formerly GM Research, and S. Robert, University of Pennsylvania. Ron Dictor is doing this.
Thank you. As Jim noted, is that focused? As Jim noted, I did this work at General Motors Research, but I currently recently switched to Amico Oil Company. It wasn't just for the sake of being able to drive a Ford Taurus, because I commuted to work for 4 years in Toyota Tercel. My heart wasn't in it. I had assistance on this project from Scott Roberts. He's a graduate student working with Ray Gordy at the University of Pennsylvania. I'll be talking today about CO characterization of rhodium alumina catalysts and Ceria promoted rhodium alumina catalysts. And the reason Ceria is chosen, I think, was alluded to earlier, perhaps, by Byung Cho in the morning session. Ceria is the principal promoter in automotive catalysts. And some of the reasons are listed here. The first one, oxygen storage, is crucial to the cycling behavior of the exhaust stream over a catalyst bed, where you go from a fuel-rich regime into an oxygen-rich regime, so to speak. And a lot of people feel that the oxygen can be stored by Ceria in its facile transformation between CeO2 and Ce2O3, and therefore be able to give up oxygen during a fuel-rich cycle so as to help oxidize carbon monoxide and hydrocarbons. It's also thought to stabilize both the alumina support and noble metal dispersions. I'll be talking about the noble metal dispersions today, and there are patents on those as well. And I mean stabilization with respect to thermal excursions, which again for automobile catalysts is very important, since cars will sometimes get up to 800 degrees C and sometimes beyond. At least the converters do. And lastly, I have stories. And lastly, listed here, it enhances water gas shift activity. Perhaps the most cited reference for this is Guan Kim's paper from a few years back from W.R. Grace. And I probably won't have a chance because of the length of these talks to talk about it, but it's my feeling that this water gas shift enhancement may actually be attributable to stabilization of noble metal dispersions, if that's indeed what how he was operating. Before I get into the data, I just wanted to show that the infrared spectroscopy of CO and rhodium is very useful, not only in identifying what the CO, how the CO is bound to the surface, but also in identifying the state of the rhodium. As you see on the top here, we have the rhodium dicarbonyl species characterized by symmetric and asymmetric bands in their 2090 and 2015 wave numbers, which is characteristic of two COs bound to a lone rhodium site. Presumably, the consensus has it a rhodium +1 ion, and that's illustrated here. If your rhodium is in a reduced state, coagulated, coalesced, you may get a rhodium CO adsorption in the linear form or in a bridged form characterized by bands near 2050 wave numbers or 1850 wave numbers here. That's the good news about infrared spectroscopy here, is that you have now essentially an atomic scale probe of your rhodium on the catalyst. The bad news, as you'll see as I go on, is that the CO tends to be disruptive to the characterization. In this first set of data, I just wanted to illustrate what the problem was that I first observed. Spectrum A here is typical of what I would observe following an overnight 400-degree reduction in 5% hydrogen, 400 degrees centigrade. And then cooling to 100 or 150 degrees C and introducing carbon monoxide, in this case at a 1% level in a flowing stream at 900 torr. And what I find is that my spectrum would be dominated almost completely, if not completely, by the dicarbonyl features. And I'd have very little evidence of the linear species, which would be here, or perhaps very little showing of the bridge species. And this suggests that I have good atomic dispersion of the catalyst. If I were to do several experiments in the course of a week, or several days, or even in the course of a day, what I would find on coming back is something more like this. And this isn't a very characterized second spectrum, but this is typical of essentially the frustration of breaking in a fresh catalyst. And that is, I lose a lot of that atomic dispersion, apparently, by the loss of the dicarbonyl species here. I do gain linear, I do gain bridge, and the simplest and presumably most correct interpretation of that is that I have lost a lot of the isolated atomic sites to larger particles. I wanted to find out what was causing that. I know that I came in very highly dispersed after a 400-degree reduction in hydrogen, and what I found out fairly fast was that CO itself the absorbed CO itself is actually the coalescing agent. In this experiment, I started off with a fresh catalyst that at temperatures lower than 200 degrees C would give me exclusively the dicarbonyl species and show atomic dispersion. But at 200 degrees C and higher, what happens when I introduce CO following that overnight reduction is I am first dominated, and this is a very crowded series, I apologize for that. I'm first dominated by the dicarbonyl bands up to about spectrum F here, which is about 5 minutes into the experiment. But following that, the dicarbonyl bands then tend to shrink away, and over the course of several hours, I'm finally left with exclusively the linear and bridged features, and have essentially a complete absence of dicarbonyl. What's important to note here is the size of this. These peaks are actually very small, and in this one experiment I see this shrinking of the absorbance values, and between experiments the absorbance values continue to shrink. Behavior for the Syria-promoted catalyst is very similar. I guess Amoco's, that last slide was GM, this is Amoco. For proprietary reasons, they try to mask the data a little bit more. In the case of the Syria-promoted catalyst, you see very, very analogous behavior, again coming in and being dominated by the dicarbonyl bands. The fresh catalyst, it turns out, in this batch of catalysts, was not even 100% dispersed initially, and it's a little less dispersed up front here, but eventually, about 5 or 10 minutes into the experiment, again, it gives way to the growth of the linear feature and the bridge feature and the diminishing, again, of the dicarbonyl. So again, I'm coalescing. The big striking difference here is that now I am left with a fairly substantial absorbance, whereas before I was very much losing sight of my rhodium, and that's why I say it was a frustration in the experiment. All's not lost, though, and there have been several reports now in the literature that have demonstrated this. If I were to take that, and this is back to the rhodium alumina, take the agglomerated catalyst, reduce it again overnight, and introduce CO at 100 degrees C, cooler temperature, 100 degrees cooler, I find something very much like what I left, and that is just the linear and bridged features. But if I let it sit in CO at that temperature for long periods of time, I start to get these nubs here, which are the bands for the gem dicarbonyl growing in. And if I were a patient person, I probably could have waited a very long time and seen this become dominated by that. Fortunately for me, I'm not that patient. So I turned to oxygen pulses, which essentially comes at this in a different direction. In one case, I introduced CO on a reduced catalyst. In this case, I'm coming down to what's presumably an oxidized rhodium state. And I introduce a brief pulse of oxygen while still at 400 degrees C, and then cool down to 100 degrees C and introduce CO. The first observation of absorbed CO is at a higher wave number than you anticipate, indicative more of CO absorbed on an oxidized rhodium species. Then eventually I get, on the same time scale as the figures we were looking at before, a very substantial growth of the dicarbonyl band. But the interesting thing here is that, again, this is very low compared to what the Syria catalyst was. And to show that, this next one, which is actually my favorite of all spectra, the Syria-promoted catalyst had a very substantial rebound from that oxidative pulse. In fact, when I gave it the pulse of like 1% flowing oxygen for 10 seconds, cooled to 100 degrees C and introduced CO, I got exclusively the dicarbonyl, no sign of linear, and a very, very flat region here for the bridge species, indicative of 100% atomic dispersion. I might note that this is actually better than the fresh catalyst was. The fresh promoted catalyst wasn't even 100% dispersed. Unfortunately, the stability of that isn't too great. If I were to just try to shut off the flow of CO to the reactor, CO will first desorb from the linear and bridge sites off the reduced surfaces, and very sluggishly will come off the dicarbonyl sites. If I try to heat it up to flash it off, heat back up to 400 degrees C in an inert, and then cool it back down and reabsorb CO, I find that just by doing that, I've introduced now linear and bridge species and have sintered the catalyst to depart. What that says is that once CO is seen in a catalyst, or once a catalyst has seen CO, I cannot shake it. Not shake it at any decent time scale anyway that's experimentally convenient. Similarly, these series of spectra here are repeats of those experiments where I reduce at 400 degrees C, reduce a sintered catalyst or an agglomerated catalyst at 400 degrees C, and then give it the oxygen pulse and cool. And I cool to these temperatures before introducing CO. And you can see here that I'm at 150 degrees C. The CO, I've come down to a much less dispersed state than at 100 degrees C where I was showing most of the spectrum before. And in fact, I can also do the same experiment by cooling to here, generating this spectrum, and then just heating to 150, I'll generate this. Well, this again points to the lack of stability of the newly dispersed species. Even though I've gained atomic dispersion, I have less thermal stability than I even started with. Before it was disrupted or destroyed at 200 degrees C. Now I can be well below 200 degrees C and find that I re-agglomerate. So the picture that I get of the catalyst, finally, is that the very fresh catalyst is very highly dispersed and will stay so even after a 400 degree hydrogen reduction. But in just 200 degrees carbon monoxide, I will find that I will agglomerate. In the case of the rhodium alumina catalyst, I may agglomerate to various particle sizes, or certainly to large particles, because I have a strong loss of absorbance. And continued heating and exposure to CO will generate even bigger particles. With the oxygen pulse, though, I can either perhaps onion skin effect the large particles and skin off some rhodium, oxidized rhodium, and generate some dicarbonyl, or perhaps selectively oxidize small particles. And you can't distinguish that in the IR. In the case of the Syria promoted, the suggestion is that these particles are either flat or small because we have, for one thing, the lack of a decline in absorbance, and the second thing, the very effective oxygen pulse, both pointing to very small particle size or very accessible rhodium. And then once you've generated this redispersed state at lower temperatures, you have a lower thermal stability, you can re-agglomerate. And I guess my time is running short. I was just going to point out that there are certain assumptions that you can make. I'll admit these are gross assumptions, but if you were to take the Syria-promoted rhodium alumina case and assume that you have 100% of your rhodium participating in both the agglomerated state and in the atomically dispersed state, participating in CO adsorption, then you can try to compare the relative absorbances of the linear and bridge species against that of the dicarbonyl. And the only reason I'm curious about that is because I always had a nagging feeling when I was doing these experiments that although my spectra were dominated at times by the rhodium dicarbonyl, if its extinction coefficient was 10 or 100 times greater than that of the other species, it wasn't telling me much. And the suggestion here, without getting into it, if you get into some of these assumptions, is that in all likelihood the extinction coefficients are probably very much on the same order, and that you don't have that situation. Finally, I'll put up my conclusions. Basically, I'm just saying that the adsorption and desorption behavior are very similar for both catalysts. The IR features I didn't really emphasize, but they are also essentially indistinguishable for both catalysts. And the agglomeration and redispersion behaviors are similar in that the onset in all instances for a fresh catalyst is 200 degrees C and are less thermally stable after redispersion and redisperse in the same manner. The big difference is that the absorbances remain much higher for the agglomerated promoted catalyst, and the oxidations are much more effective for that catalyst. And my suggestion is that the particles are indeed much smaller, or much smaller in the case of the Syria promotion, and that explains both those behaviors. And lastly, as I referred to earlier in the talk, some of the reputed benefits of Syria may actually be attributable to this oxygen being able to access highly dispersed rhodium in its cycle of automotive operation. Thank you very much.
I have two questions. First one is that a lot of your CO results for rhodium seem like your catalysts are swimming against the tide of what a lot of other people are saying, and that when you put CO on rhodium, you tend to disperse the rhodium, and that
At
people
low
have seen.
temperatures.
Yeah, that's what I was going to ask you. Is
No,
we've
that
done
was-
it, well, we've gone up to 150 degrees and we don't see the effect you have. So I was going to ask if you think that it's an effect of maybe doing it in flow as opposed to doing it in static, what most people have done.
Well, in answer to that question, that does concern me at times, the flow versus the static. The static
Because
is
you
nice
may
and
have a better
do it.
chance of sintering if you're. I think that the flow situation might
Well,
give you a better chance of
The
sintering.
flow, you're continuing,
Because we see the
continuing
exact
counting it
opposite.
with CO, you'll always maintain a CO atmosphere above it.
Right.
You're not just pulsing onto it. So yeah,
Yeah.
it's a more reducing environment.
And the other question was just in terms of your terminology and talking about stability, it sounds like you want the dicarbonyl species, but is there really any evidence that that's the species that rhodium in a partially oxidized state is what's necessary for the reaction, especially for the NO part? And also the reaction results that other people show, not IR results, they don't seem to show changes in the activity that would match your change, the stability changes that you see.
Actually, I had seen a little bit of that similar behavior. If I were to do CO oxidation over a fully sintered rhodium aluminum catalyst, without seeing any really appreciable change in the catalytic activity, I can then just shut down the reaction, go back and try to characterize the catalyst and find that I've generated a lot of dicarbonyl, making me wonder whether it was somewhat incidental, whether it's just there but not really playing a big role. This is a controversy that kind of went on between a few of us at GM, and basically I kind of arrived at the conclusion that probably, at least for CO oxidation, both forms of the dicarbonyl and the supported and the agglomerated surface are probably active for CO oxidation, one perhaps more so than the other. Part of the frustration is that a lot of the experimentation then goes well beyond these kinds of temperatures. And while it's fun to characterize rhodium at these low temperatures, you ultimately have to ask yourself, what the hell does it mean, excuse my language, because a converter will typically operate at 500 degrees C, light off at a couple hundred, and take you up much higher.
And you can do the CO oxidation reaction just as well with just platinum, and you don't need a dicarbonyl species in that case to do it, or a partially oxidized species.
More interestingly, though, and this gets back to some of the observations that Von Kim had made with the water gas shift, is I think the dicarbonyl or dispersed species is probably responsible for a lot of water gas shift activity. But when you have a small particle size, something like nitric oxide may actually disrupt your particle, and I think in that instance you really want the contiguous rhodium surface for the dissociation of nitric oxide, and going to a small particle actually might be detrimental. Again, it's seeing it under reaction conditions, different story.
Ron, I'd like to question the thermal stability of your dicarbonyl and linear species. I guess that you're coming to the conclusion that the dicarbonyl is thermally more stable than the linear species. That is completely in reverse of what we see. For a reduced rhodium catalyst, if you put a pulse of CO in there at 200 degrees centigrade, we get only the linear species. And if we do the same experiment at room temperature, we get the dicarbonyl plus the linear species. Now, we haven't done the TPD to characterize it. Perhaps somebody else has done. But there seems to be a big discrepancy here, and I think that Worley has gotten the same results that we have in terms of the thermal stability of the dicarbonyl species and the linear species.
I don't necessarily follow what you mean with the pulse.
You have
Putting it in because
catalyst and you're throwing helium through there, and then you put a pulse of CO at the infrared at 200 degrees, and all you get is a linear CO species. If you do that at room temperature, you get both the dicarbonyl and the linear species.
I guess what I don't know is the previous history of the catalyst. I mean, in one of those slides, I had exactly the same thing. In the highly dispersed case, even for the highly dispersed case coming from an oxidized state of rhodium, the development of the dicarbonyl bands wasn't by any means instantaneous. It took some time. I'd have to reduce from an oxidized state or break apart something from an agglomerated state. On shutting off CO, I would never see anything but essentially immediate disappearance of linear and bridge species with dicarbonyl essentially hanging tough. I could shut down my reactor, allow oxygen in even at room temperature, and come back to it sometime later and still not have shaken carbon monoxide.
What I'm talking about is a very typical catalyst, a 42% dispersed catalyst on catalyst cell, rhodium catalyst cells. And it's been reduced to 400 units in hydrogen. So I'm
it's just the direction you're coming from. I wasn't sure, what it show up, because I can see similar results. It will, the linear enriched will, given all sites available in a pulse, seem to absorb and show up preferentially. But once all species are there on the absorption, I wouldn't see anything but what I've shown, or what I mentioned.
Thank you, Ron.